Hello, and welcome back to the second episode in this 8-bit breadboard computer series that I am currently doing. Today we're going to be building the clock module for the computer running at 20 megahertz, but it will be clock divided down to 5 and 2.5. This is the oscillator that will drive the clock, and I will hopefully be implementing a push button switch that will be able to do single stepping instructions. So let's get into it. Alright, so we're looking at the 3 clock signals of the computer here. This first signal is the main clock, the clock that we use for most operations. It is running at 2.5 megahertz, as you can see in the upper left corner. Sometimes it does flick to like 52.5 on the duty cycle, a little bit off, but generally it is a pretty perfect clock cycle. Then we're looking at the not clock, the inversion of the main clock. As you can see, it's high when the other clock is low. It also has some fluctuation, and it will be mainly used for the control module and stuff like that, so we can prepare instructions on the first half of an operation. Technically not first half, but like we can prepare an operation before the main clock pulse. And then the half clock, this is also mainly going to be used for the control module. It's going to be used to make sure we can get multiple things done within one actual clock cycle. It'll be used for like the program counter. Incrementing that doesn't take 200 nanoseconds. It doesn't even take 100, so I can do it twice in there. In that way I can access like the RAM twice and get multiple instructions. Just makes that step going to be a lot faster. So that's the reason for all of these signals. Alright, those are the main clock signals for the computer. Now that I've done that, let's talk about the circuit for the computer. Alright, so the circuit is mainly based off this oscillator, the 20 megahertz here. I'll put the parts using this build in the description, but this is the 20 megahertz oscillator. This is the 74161 AC, and that's the logic. I'm using mostly CMOS, HC, and AHC, AC and AHC. This is the 74161 counter, and it works as a clock divider when I used it here. So I have the 10 megahertz output, 5 megahertz output, 2.5, and then 1.25 megahertz output. That's the main purpose of that. There I have decoupling capacitors, standard 0.1 UF, microfarads. Then this is the inverter I use to get the not clock. I just invert the 2.5 megahertz. That's the inverter used to do that. It's really not used for anything else here. I should tie that line low as well to prevent noise on the chip. So that's the main circuit. I have bigger decoupling caps for the board, an LED, just more of an indicator light. It's a pretty simple circuit, but it gets the job done. So now let's talk about overclocking. Overclocking is theoretically possible. These chips often run a lot faster than their propagation delay time, however you say that word. Their delay is supposed to. So I think it's possible, especially if I was just using these chips, but I'm not. I'm using RAM that can take 50 to 70 nanoseconds to access, and you don't want to push that. So it might be possible to run it at 5 megahertz with the main clock and 10 being the half clock. It might be possible, but I'm not going to push it. I'm going to try and get it running at this 2.5 megahertz clock speed before trying something like that. But I will be trying that in a future video because I think that would be a cool possibility for the computer. Alright, so now I am going to be showing the schematics for the computer, the block diagram, and more thoughts about the architecture. So as you can see, this is the block diagram for the computer. We have the ALU, the registers, the register decipherer, which will take part of the instruction stored in the instruction register and tell which register to use. Obviously, the instruction register itself will be connected to the control word because I couldn't decipher it and get that code without the instruction register. So it has to be in the control word. It will also be there. Then we will have the instruction register I've talked about, the interrupt flagged register. This will connect to the main data bus. The RAM, storage, data segment. This is going to be used for the .data directives I talked about in the last video. It is a segment register, so that way I can put a value in that register and any address will just access from that plus the address. It's the top 8 bits of an address. Then we have the program counter, the stack pointer, and the clock, which I have been building and finished for this video. So that's the main gist of the architecture. I talked a lot about the individual operations last video, but now I'm going to talk a little bit more about stuff I didn't fully touch on, like the flagged register, and a bit more about the register decipher, and more about the control word. And that's probably going to be the main thing that wasn't shown in the last video. So the first thing is the flags. I'm going to have the 4 flags commonly used: overflow flag, the sign flag, the carry flag, and the 0 flag. These flags will be used for all sorts of operations, jump operations, and they will be very useful in having the full instruction set very easily implemented and not having to do challenging stuff with one jump. Even though it is still turning complete, it's still possible. It's a lot more challenging. And then the register decipherer, it will take in 2 8-bit codes and get the register output for it. So that way I do not have to mess around with the control word and using up like 10 to 15 control word bits. And also having a lot of different instructions just to move registers. Instead, it can just be a different code for that. So that will be very handy for that. And then the ports. So I mostly talked about these last video. The 2 LCDs are simple. The PS2 keyboard is a lot more complicated. I'm going to be using shift registers and to do the PS2 interface. And it's not even PS2. It's probably going to end up being USB, but it might be PS2. So I put it as PS2 because I think that would be easier to implement, but I might have to change it to USB because that's the parts I would have and the stuff I would have to do that. And then the final port would be the interval timer, and I'll actually talk about this and how it will work. So it will be able to set a time, and it will count down and give an interrupt to the system, and then it will be checked and handled. And if you want to have multiple delays from different programs, you can do that by just doing the subtraction, and then after the first delay goes off, the next one would be immediately put in by the operating system, getting fairly good delays. Obviously, it'll be off by a couple microseconds. So it's not going to be perfect. It's not going to be perfect in terms of instruction cycles, but it'll be very accurate, a lot more accurate than a human could be able to tell. So those are the main things I didn't touch on in the last video. So that's the main function of the architecture. Now I'm going to go into a little bit more depth about the control word. So far I haven't finished doing the control word, but what I know so far is there's going to be 8 writs for the actual register encodings, like I/O and stuff, not for deciding which register, but for like if it's inputting, outputting, or what half of the register you're using, what part of it. So just like the 8086 architecture, the x86 architecture has, you can use the top 8 bits and the lower 8 bits of a register. That is going to be a functionality in this system as well. There's going to be the flag input output for like push F, push the flags, the program counter and output and input. The ALU operation is actually going to be in the control word. So like addition and subtraction will be in the control word, and then further deciphered in the ALU, but that will be from multiplexing, so it will be fairly fast, or demultiplexing. And then we have some bits for the instruction register in there, controlled data versus data bit, I/O bit, and there's going to be clock bits and stuff like that. That's going to be port stuff. And so those are the control bits I have so far. Obviously there'll be some for the RAM, probably more for the ports. There's going to be some for like the stack pointer, but that's the general functionality of the control word. And that is the main functionality of the system. So I hope you enjoyed this video. I hope it was helpful for understanding more in depth about the computer. Next video I am going to be uploading either next week or the week after that, and it is going to be about the program counter, the next module I will build. I hope you enjoyed this video. Please like, subscribe, and leave a comment down below. Thanks for watching. See you next week.